In this demonstration, you'll learn about setting up a moving and deforming mesh problem in Fluent. I'll begin with two quick animations just to show you what it is that we'll be setting up later on. Here you can see the velocity profiles develop as the piston pushes the air, forcing open the reed valve, and the valve closing as the piston slows to a stop. Notice how the velocity is 0 in this area above the valve. This region is defined as porous media, and you can think of it as a gasket that's stopping the flow. The second animation shows the moving and deforming mesh that helped Fluent calculate the velocity profiles in the previous animation. This tutorial will give you the basic information you need to be able to properly set up a dynamic mesh problem. As such, I'm glossing over some of the other settings. I've already loaded a case into Fluent and specified a few settings including the transient solver, energy and turbulence models, and air as a compressible fluid using the ideal gas law. I've also already defined the region above the valve as porous media using a UDF. I've split the domain into several different cell zones. This first area, filled with hexahedral cells, is where I'll be using the layering technique. This second region, containing the valve, is divided into 3 zones: the prism layers around the valve, the triangular mesh zone, and the prism layers on the stationary walls. This final area is the stationary mesh outlet. I'll go into greater detail about these zones while I'm defining the dynamic mesh. The next part of the setup is the boundary conditions. The only setting to note is that the exit here is set as a pressure outlet with 0 relative pressure and reasonable backflow turbulent quantities. Now, to define the dynamic mesh for this case, I need to enable dynamic mesh. I know that I'll be using layering for this zone and smoothing and remeshing in this zone, so I'm enabling all 3 of these options. I also know that I want this valve to open due to the forces acting on it, which means I need to enable the 6 degrees of freedom or 6DOF solver. I'll start by defining this piston's motion by creating a dynamic mesh zone. And this boundary is called inlet. This inlet will be moved by rigid body motion, and it will not be moved by the 6DOF solver. Instead, I'll use a profile to describe the motion of the piston. This profile specifies when the piston will begin to accelerate and when it will slow to a stop. Now that it's loaded, I can set the motion to this profile. The last thing I need to define for the piston is the cell height, which is the height normal to the direction of motion, and it's used in the layering technique. This cell height of 0.01 meters is the width of the cell wall, here. It's important to have the same cell height on each cell row throughout the domain. This zone is called fluid layering, and the mesh will be deforming. I want to ensure that only the layering technique is used here, so I've disabled smoothing and remeshing. Next, I can go on to define the motion for the valve. It'll be moved by rigid body motion, and in this case, I'll be using the 6DOF solver. Now I need to point to a UDF that describes the 6DOF settings. I can give you a quick look at the text file for this UDF. This specifies the mass of the valve. This is the moment of inertia. These specify which degree of freedom is free to move. As you can see, it's only free to rotate about z. X, Y, and z translation is fixed, as is the rotation for x and y. I also have a simple sine function to define the gravitational force on the valve. Now that I've loaded this UDF, I can select it. The final thing I need to do is remove the cell height, as it has no meaning here. And create. I also want the prism cells around the valve to move with the valve. This is the prism layer around the valve. It'll be moved as a rigid body, and its motion will be calculated by the 6DOF solver. But I don't want the forces and moments of this zone to be taken into consideration, so I've enabled passive zone. The next zone that I want to specify is fluid remeshing, and as I display this zone, you can see that it's filled with triangles that will be deforming. For mesh options, I want to use smoothing and remeshing. By clicking Zone Scale Info, I can see what properties the mesh already has to populate the minimum length scale, maximum length scale, and the maximum skewness that will be used to determine when to remesh this zone. Now I can create the zone. The final zone I need to specify is fluid stationary prisms. This zone just needs to remain stationary while the mesh around it is moving and deforming. This concludes the local setup for the 6 dynamic mesh zones. I encourage you to watch the follow-up video to this one, which covers other good practices for when you are defining a dynamic mesh problem. I'll pick up where I left off in this video.